So hope this is visible, right? Is it visible?
Yes, ma'am.
Yeah. So, with respect to control dependence, yesterday the problems, normal problem that may occur is one is the exception behavior. The other one is the data flow, I think. So, and I mean, we've seen a few examples for those things also. And there is another problem. Suppose we have an example like this. So, the add view. So, branch equal. We are okay. We have these instructions. So yesterday we have seen, right, if something because if the branch is true, it will go to this part and will execute, or else if it is false, this statement will be executed. So yesterday we have seen, suppose if we take these two things and if you executed before, so probably, right, there may be some problem associated with that. So in this example, suppose, right, if we are just taking these things, this statement, assume that d sub and d add, if you are taking those two statements and if it has been executed before this branch instructions, will there be any error? Will there be any error in correctness of the program? Is the question. Okay, so just simply write, this is under the control of the branch statement. So if you are, suppose if you are just taking this statement and it has been scheduled before the branch statement, so now we need to check whether it is going to be correct or wrong. The only problem associated here is, see here this registers R4 and R5, right? So these two, if suppose in later case of the program, if R4 or R5 are used, so definitely if replaced, if scheduled before, you may so no correctness of the program. Do you agree that or not? After this statement, if somewhere if R4 and R5 we are going to use, so definitely, right, definitely there won't be any correctness, because maybe it depends upon the branch, if it may take or it may not take. Okay, so such cases, right, there won't be correctness. Suppose if R4 and R5 is not used anymore, after this two statement, if R4 and R5 is not used anymore, if I is trying to schedule this before, will it work or not? Will it be correcting or not? Here I'm trying to say not used means here this variable is dead. So in this case, after this, we are going to use it. So this is going to be alive after this also. So in such cases, right, we cannot schedule it. We cannot schedule before the branch. We cannot take the statement which is under the control of branch cannot be taken out of that. But this case, if R4 and R5 is dead after this, so even if you are just trying to schedule it, so it won't create any problem. So this they are saying it as this part, right? Whether the value will be used by the value is used by upcoming instruction. If the value is used by upcoming instruction, then we can say it is as the way it is liveness. Okay, this one. Okay, if suppose I'm just saying it, if R4 and R5, if it is going to be used by the upcoming instructions, then it's liveless. If you are trying to schedule it, it will be a correct programs. If this going to be dead, even if you are trying to schedule it, it won't create any problem. So it is all depends upon the situations. But it, because last yesterday's example, what we discussed is, If you are trying to take any statement which is under the control of branch, and if you just place it before it, so you may get either an exception behavior or you may get some data flow error. Okay, but according to these examples, it is all about the liveness of the registers. If it is going to be used by the upcoming instructions, then scheduling may be a problem. If it is not going to be used, so we can schedule it and accordingly we can able to do it. Got it? Yeah, I think this liveness, this part I forgot to explain. That's it. Okay, so now right, today's class we will go for this compiler technique. How to use the compiler techniques for exposing instruction level parallelisms. Now we are seeing, so there is a data dependence. So one or other way we need to avoid that. So which means we need to go for scheduling. Only by scheduling the instruction. Don't think that scheduling something like round robin, those kind of things. I mean rearranging of instruction. Here scheduling is the rearranging of instructions. So thereby, right, we are trying to reduce the number of clock cycles essential for executing that particular block of code. So that's the aim over here. And when you're trying to incorporate instruction level parallelisms, or at the stage that the pipeline has to be full. It shouldn't wait for anything. That idle time, right? That start should not be there. So it has to be full for all the time. So that's the aim here. Okay. So let me go with an example to explain how compiler helps out to exploit the instruction level parallelisms. So this code, I think every day we are trying explaining this code. So we have an array and we are just taking it assume some memory location. So from that memory locations, the data is so x of 0, x of 1, the data is there, and it is going to be some floating variable. So it is like 10.2, 11.5, something, some float variables is there. Okay, so this has to be, I mean, we have to load the data from this location. Assume it will be added with some scalar values. Let it be as 10. So after this, right, it will be stored back here. This is the operation. It is happening. Okay. So just loading the value from the memory, adding to a scalar value, and again we need to store it back for this n number of elements. And here it is going to be 1000 elements. Just for 1000 elements, this process has to be done. So this is the equivalent MIPS code for this. For the C programming. So what I mean, this was the same code. So load double. So it is loading the data from the memory, and once it has been loaded, you people may have a doubt why here it is registers. This is the normal registers. This is the integer registers, and this is the floating point registers. Okay, because address won't be address. I mean, when you just go with the memory address, none of the address will be in floating points. Okay, it will be in decimal only. Okay, so that's why they have just gone with the integer registers. So they are loading the data. Once they load, they are adding the data with the F2. Okay, so this one F4 will be stored, F0 plus F2. So before that F0, just we are loading the data which is there in the location, and it has been added. And finally, this F4 is stored to the location R1. Once it is loaded, we are just decrementing the R1 by 8. I mean, we are just lowering the address, and then assume that the R2 is the end of the elements. We are comparing it, and we are branching it again. So this loop is going to execute for what? 1000 times. Clear. So basically, suppose when you just go with the pipelining, I mean, on the day I said we have a fetch, we have a decode, we have an execute stage, and a write back. Sorry, this is memory. And a write back. So fetch, decode, execute, memory, write back. What is this? This is for integer. Suppose if we have an integer unit, and this is for the floating So this one, fetch, decode, execute. Suppose if you have load, assume that you have a load instructions. Okay. So the thing is that we are going to load the floating point value to a register. I mean, from a memory to a register. Okay. So we are not doing any floating point operation. Our floating point operation is not carried out. So if suppose if you have a load or a store instruction, where it goes in this part, above part or below part. Guys, are you there? Okay, see, I think if suppose I have a load instructions, so it will be fetched and it will be decoded. So it knows that it is the load instruction. So it will go for the execute stage. So what is the role of execution in load store instructions? So if you take a load store instructions, what is the use of ALU here? For load store instruction, will it be useful?
Computing the memory address.
Yeah, correct, right? It is going to compute the effective address. Clear? Because you know that, right? Suppose if you have an array, you know, right? It will be added a plus 0. So something it will be done, right? To find out the address, because we are interpreting. In case of a C program, we are interpreting like this. So to compute the effective address, we need this execution part. And then, right, the fourth cycle, it will go for the memory, and finally it will write back to the registers. Okay, so this is the load store. And suppose if it is going to be a floating operations, so probably, right, for executing, clearly it takes 4 cycles. I mean, by default, it will going to take 4 cycles. Okay, if it is a floating point operations. Now, right, when you have an instruction like this, so this instruction is the load instruction and this instruction is the add instructions. So this is going to load the values and this is going to perform the floating point operation. Okay, so definitely through this instruction we get to know there is a data dependence, right? Between this and this we have a data dependence. So until this completes, this has to get wait. Do you agree that or not?
Yes, ma'am.
Yeah? Okay, until load has finished, this should be that. Okay, so let me see. So when you just go with the load, at the fourth cycle itself, we will, at the end of this stage, we will have the data. Okay, so we will have the data and finally, right, it will move back to the registers. Okay, at the end of the cycle, it will be moved to the registers. There is some concept like, I think it is not covered in this book, but it is something like forwarding. Some option is something like data forwarding. What that says, suppose, right, if you have like this, assume this, R2 equal to plus, I am giving like this. Okay, so this is the add instruction. Actually, this add instruction is doing this. Suppose subtract instruction, it needs the R2. Okay, so I mean, when you just go with this case after executing itself, right, we get to know the these things, right? R1 plus R2 will be no only during this fifth cycle only we know the data will be reflected in the registers R2. So sometimes, right, what they are doing is after computing this, immediately it will be forward. That they are doing the data forwarding. So instead of R2, this may be as R1 plus R3. So this they are saying it as data forwarding. So they, I mean, which means, right, they are not waiting till it write back to the register. From register, they are not fetching it out. Once the computation is done, that the data can be forwarded. So that they are saying it as data forwarding. Okay. So similarly, right, in this case, when we go with the load instructions, okay, we will take this at the end of the fourth cycle. We got the result. So, but when you just take the add instructions, okay, when you take an add instructions, so when I mean the third cycle itself, we need the data. You understood or not? At the third cycle itself, we need the data, but only at the end of the fourth cycle, we get to know, right? We will get the result. So how many cycles it needs to wait? You understood what I'm saying? See, floating point I'm just trying to perform. First instruction is the load instruction. According to this example, write it. So first instruction is load instruction. Okay. Next instruction is add instructions. So whatever the value produced by this is going to be used by this instruction. That is B. Okay. This is instruction 1, instruction 2. So instruction 1 is the load instructions. It will go in these things. Clear? So only at the end of the fourth cycle, we get to know, right, the data may be available. At least if you remove this, at least this stage, right, through data forwarding, we may know that at fourth stage, you may get it. So meanwhile, the second instruction will also be scheduled. So one cycle later, it will be scheduled. So it will be there here. And at this stage, it needs it, right? Here it is in fourth cycles. So here, right, it will be in the third cycles. After fourth cycle only, we need the result. You got it or not? After fourth cycle only, we will get back the value of this F naught and it will reach this floating point unit. Then only, right, the add instruction has to proceed. So which means it needs to wait for one clock cycle to get it. So this is the information that is provided in this table. I mean, I'm just giving the explanations, how it has been arrived. So see, suppose if you have a floating point ALU operation, assume that you have a floating point operation. If this output of this floating point operation is going to be used by other floating point operation, how many cycles? There is a latency. This many 3 clock cycle it has to wait. Keep remember. Clear? Floating point, and if output of one floating point is going to be used by the output of other floating point operation, it needs 3 clock cycle. Similarly, a floating point operation, output of floating point operation is going to be used by store double. How many cycles it needs to wait? It needs to wait 2 cycles. So this input will be given during examinations. So you don't worry, but I just given an explanations how it has been arrived. Okay, so this input table will be provided. Similarly, if a load instruction is followed by an arithmetic instruction, it needs only 1 cycle. If a load is followed by a store, it needs only 0 cycles. Okay, so this is the actual input. Now, right, we will take this example, the same example, this example. Okay, so the same example, we will see how to schedule it. So according to that instructions, we have load F naught comma 0 of R1. Next, add a double F4 comma F naught comma F2. Next, store F4 comma F naught of R1. Next, D add. Okay, listen. Okay, this is at the first. Assume that, I mean, just I will say, I'll say each thing is going to have 1 clock cycles. So initially, right, we have this instructions. So this is what this is the load instructions, and this is the floating point ALU operations. So from this table, if a load instruction is output of the load instruction is going to be the floating point, if it is going to be used by the floating point ALU operations, we need one, I mean, it has to wait for 1 cycle. So probably, right, we need to introduce the stop here. You got it or not? Since it is this load, output of load is going to given to the add instructions. So 1 cycles it has to wait. So we have 1 stall here. Next, add instruction. This is what a floating point ALU operation, and it is going to be used by double. So how many stars it needs from the table? Can anyone say?
2.
Here, right? A floating point operation, output of the floating point is used by the store instructions. So it has to wait for 2 clock cycles. So probably, right, you need 2 cycles. Next, store to deadd. Did I give anything? So nothing. Okay, so there is no options. So probably, right, there won't be any cycle. So no dependencies. So automatically, right, it will get executed. And so when you go to between this and this, here you have, you may check there is a data dependence. Do you agree that or not? Because this output of R1 is going to be used by this. Now the question is how many cycles is going to be used. So here they haven't mentioned about any branch instruction in this table, but yesterday I have discussed when the branch instruction, how do they know at which stage they know?
Decode.
I mean,
ALU output, ma'am.
yeah, no, you have like fetch, decode, execute, so and so, right? When you go with the, I told you, the branch instruction at the decode stage itself, we should know it. Then only, right, the branch prediction will happen. It won't wait till execute stage or after that. Okay. So when you just go with the branch predictions, I mean, when you have a branch instructions during decode stage itself, it should know the value of R1 or all the values. Then only, right, using branch prediction techniques, it will switch over to the corresponding position. Yesterday we discussed the pipelining flushing. Okay, so since it is happening at the decode stage itself, only one instructions we are going to flush it out. If suppose if it is not at this stage, after this only, so we need to flush 3 instructions. I think I explained yesterday the similar cases here. So only during branch. So branch instructions will be decoded and the input is needed at this stage itself. Okay, so if that is the case, how many cycles it has to wait? Because 1 cycle later it is going to be, it will enter into the pipelining. Okay, so probably, right, it needs to wait for a single stop. Okay, since, right, it needs to, what to say? Since this branch is to be executed in decode stage, so after, it has to wait for 1 stop. Understood? So I think, right, this one. So this is first and the second, 3, 4, 5, 6, 7, 8, 9. So on the whole, to execute a single loop, this is for only one element. So to execute one element, so how many cycles we needed? How many cycles is needed? 9 cycles. So assume that each instruction is going to take like 1, 1, 1. So totally we have 9. So altogether, right, 9 cycle is needed to execute this code for single element. That too without scheduling. We haven't scheduled anything as it is, right? We have written. So when you try to calculate this, so what is happening is it results in 9 cycles. Suppose if you are going for scheduling, so the same programming, if you try to schedule it with scheduling, you just have a cross check, we have a load, so output of this has to be dependent on this. Similarly, output of this has to be dependent on this. How about this instruction? Is this instruction is dependent on anything? This instruction is dependent on anything?
No, ma'am.
No, right? So what we can do is we will go for scheduling it. So just some instructions we are revamping. Suppose we have like this, F naught comma a rough one. Simply, right, I'm just doing this. the de-add instruction I'm bringing before. Okay, so now right, what is happened here? I just scheduled one instruction which is here. I just scheduled it here. That's it. Nothing more than I did. Okay, so only I just replaced here. So when you go with this case, so load instructions will load it. So load followed by the integer. So again, right, the cycle is going to be 0. Sorry. When a load is followed, it's going to be followed by the integer. So it is going to be, there is no stall here. And again, previously we have checked when the output of load is going to be done to the add, it needs to wait for one stall, but we have tried to fit that by using the other instructions. So probably, right, so I mean when you just start count the clock cycles, so this is going to be 1 and this is 2 and this is 3, and here the output of this is going to be depend by add. So you just check it out. Floating point is going to be used by the store, so probably we may have 2 stalls, and store is there. And here, right, when you go with the R1, the R1 is depend on de-add. On the previous case we have checked only one cycle, I mean it has to wait. Now, right, it has been executed long back itself, so you no need to wait, so immediately it may get the output. So this is 4, 5, 6 and 7. So in the previous case it is 9 cycles, so now, right, it is going to be 7 cycles with scheduling. Yes, 7 cycles with scheduling. Got it or not? So previous case, as it is nothing, no scheduling is done. So based upon the cycles stalls we have calculated, it is going to be 9. But when you just try to schedule the code, that means we are just trying to rearranging wherein right, we are trying to correct, I mean replacing some stalls. So in such cases, right, it has been reduced to 7 cycles. Till this, any doubt? Have you understood or not? See, this table will be provided to you. So based upon that, you just try to put it out. So one thing you need to know is this one. If the output of integer is going to given to the branch, there may be 1 stall because it is going to happen at the decode stage. You need 1 stall. So the remaining input is provided in this table. So based upon that, you just try to fill the stall and calculate the total number of cycles. Once done, you try to schedule it. I mean, you try to remove some stalls, wherein for that we have to rearrange the instructions, and you just try to calculate it. Okay, so I hope you don't have a doubt. So I'm just proceeding to the next step. So when you just look at this instruction, we take this program. Actually, what it has to be done, it has to load the value and it has to add to the scalar value, and then it has to store back here. So loading, adding, storing is very important. How about these instructions? What these instructions are? This de-add and BNE. What those instructions are? So if you take these instructions, this de-add IO and BNE, those two are branch overhead instructions. This is because of branch, we are including those two instructions, isn't it? So it is similarly as we are doing it, we are decrementing one things, and this is by we need to compare, and accordingly we have to proceed it. Okay, I less than something, or there is some condition greater than or equal to 0. Okay, so these two are the branch overhead instructions. If you take this program, totally, I told you we have 7 clock cycles. Out of these 7 clock cycles, actual work is load, add, and store. Only 3 cycles is for actual operations, and the remaining 4 cycles is for what? Branch overhead. Okay, so out of 7 cycles, only 3 is for actual operations, and the remaining 4 cycles is for completely for the branch overhead. Okay, so in that, right, one is for what is this? Two instruction, one cycle, this one cycle, and 2 stalls. These 4 are unwanted things. So what we need to do is we have to eliminate those things. So what is the solution for eliminating those things? So one simple techniques that is provided by compiler to avoid this loop overhead instructions. Okay. So to avoid loop overhead instruction is loop unrolling. This is the important case. Understood? Okay. So when what they're saying is, right, every cycles, every cases, 2 cycles are wasted for this branch overhead instructions. So to avoid that, we have to go for loop unrolling. So what is loop unrolling? This is something sounds like this. Say for example, if you have like this, so I less than I less than 1000, I plus plus. I mean, normally we will do like this, isn't it? Like a of I equal to a of I plus 10. Instead of that, you can do like this: a of I plus 1, a of I plus 2, okay, a of I plus 3. So, but now, right, since 4 times, this I has to be incremented for 4 times, I equal to I plus 4. Okay, since 4 times, so it has to be incremented for 4 times. So this what the thing is. So what is the observation you can make from this example?
We can reduce the
Because for every element, I told you, right, for every element, how many cycles it is happening? 7 cycles, isn't it? For every single element, 7 cycle is happening. So out of that, only 3 cycles are valid things. The remaining 4 are overhead instructions. So what we are trying to do is we are trying to unrolling. So we are trying to unrolling. So thereby, right, in a single branching instruction, we are trying to perform 4 operations at a stretch. So if you are trying to do, so how it will be reduced? We will see that. Okay. So this is an example for loop unrolling. This is the way we are going for loop unrolling. So when you are doing loop unrolling, the branch overhead will be reduced. That's the major aim. Okay, branch overhead you understood, right? At least you forgot about the stall. At least these 2 things. We need to decrement and we need to branch. So for every element he has to do, but this loop for every 4 element we are going to do. Understood or not? So that is very important here. So we are just trying to avoid this branch overhead when you just go for loop unrolling. This is an example for loop unrolling. So this is the same example. This is without schedule. Okay, the most important question that may arise is when you are unrolling, Here I have just, how many times we need to unroll will be the questions. Understood or not? Okay. So, now right, I just made it for 4 times. So, suppose if the loop is going to execute for 5 times only. So, how many times we need to unroll? It's going to be a question. So, for that, right, normally, right, what they will do is, so they will take something, so n mod some k times. Sorry. And if there is any balance, so that n divided by k times, so that has to be repeated. So assume in our case, suppose I have 1000 elements to be processed, so I'm just making 4 elements, so 1000 by 4, probably, okay, you will get 250. Okay, so 250 times, right, we need to unroll it. I mean, totally, like the loop is going to for 250 times. So instead of 1000, got it or not? Instead of 1000, so what we are doing is just we are, unrolling for 4 times, and thereby, right, only 250 times the loop is going to get to execute. Suppose assume if it is going to be 1002 or something. So again, right, if it is divided by 4, you will get 250, 1002, and so this is mod. Sorry. And the remaining 2 times has to be separate things. You got it or not? So this is the way, I mean, this has to be determined properly. How many times, right, we need to repeat the loop. So we take the same example. I told you, right, we are just loading, adding, storing, that's it. And this thing has to be very careful, and we need some extra registers to store the result. Previous cases we have used only F0 registers. So this 3 statement you are clear. Now write again the second element. Assume this is the 1000th element, or sorry, 9999 element, and this is 998, and this 3 is for 997, and this is for 99876. Okay, A of that element. So what is happening? I mean, they are using some register storing it. After that, right, we have F6 minus 8. It has to be decremented minus 8, and then it has to be 16, and then minus 24. Since we did 4 elements, so R1 has to be subtracted with 32, and the loop has to be repeated. Okay, so this is without schedule. Now, right, you just calculate how many cycles required for this uh, program, for this this is loop unrolling without schedule. Okay, this is loop unrolling without schedule. So now, right, you just calculate how many cycles will be required here. Make it fast. I will just once again, I put the table for your reference here. Just you calculate how many stalls will be there for here, and what will be the total number of cycles. Make it fast. Okay, you have 40 instructions. I want to 4, 5, 6. Okay, 12 plus 2, 14. So on the whole, you have 14 instructions. How many stars will be here? So 20, we have 14 instructions plus stars. The same table you use it. So load, if the load is all followed by an add, you take this. If your load is followed by a floating point operation here, if the load is followed by a floating point operation, you need 1 stall. So here, right, you may get 1 stall. Next, If a floating point operation is going to be followed by a double, it needs how many stalls? 2 stall. So here right you have 2 stall. So this for load to store to load, there is no stall. Similarly, the same thing, repeat it. So here you have 1 stall and here you have 2 stall. Here also 1 stall, you have 2 stall. Here 1 stall and here 2 stall. And this one, right, we have 1 stall. So how many you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 30 installs. At least have you calculated or not? Did anybody did?
Yes, ma'am.
Or any doubt? Hey, please you respond.
Clear, ma'am. Totally 27, ma'am.
Understood or not? So totally how much you have? 27
27 cycle.
clock cycles, isn't it? Because 14 instructions, 14 clock cycles, and for stalls we have this. So on the whole, right, we have 27 clock cycles. So 27 clock cycles for how many elements?
4 elements. 4 elements.
4 elements. Okay. But still again, this is loop unrolling without schedule. Now, right, we will go for the same case, loop unrolling with scheduling. So we will try to schedule the instructions. So when you just go like this, so simply right, they made this load, they have scheduled it, all the load instructions they bought before, followed by an add instructions, followed by the store instructions, and in between they added this. So now you just check, this is loaded and the output of this is used by this add instructions. So in the previous case, this load is going to be used by add, we need 1 stall. Now, right, before executing this add, we will got the result because in between we have 3 cycles. So probably this may get the output. Similarly for all the cases. So there won't be any stall at any case because even right, after adding this, you take this. After adding this, we need to store it. So there, right, we have 2 stalls. But after adding these 3 clock cycles, after that only our store is going to come, where store comes into picture. So thereby, right, here also the stalls will be, there won't be any stalls. Got it or not? So similarly, these things, they bought it here. So before 1 cycle we need it. So we have 2 cycles. So there won't be any stall. So this code just the compiler has scheduled like this. So when it is trying to schedule it, so on the whole, how many things we need?
14.
Only 14 instructions. So probably right, we have 14 cycles. This is for 4 elements. Suppose if it is for 1 element, so obviously right, it is 14 buffers. So approximately right, it comes around 3.5 cycles. But when you go with the first example, so what has happened? We got here 9 cycles. Okay, we got 9 cycles without schedule, and with scheduling we got 7 cycles. And when it just gone for loop unrolling, it has been reduced to 3.5 cycles. You understood or not? So this is the way that compiler is improving the performance by scheduling the code. Any doubt? So the same thing you need to do. So I mean, during examinations, so what type of questions you may get in this topic is they will give the similar code, right? Not a similar code, I mean similar kind of problem, and they will give this table also. So based upon that table, you have to go with all the 4 cases, with scheduling, without scheduling, loop unrolling with scheduling, loop unrolling with scheduling. So there they may tell about these things also. What is that? How many times you need to unroll, all those information will be provided. So simply right, you need to do it. If you have any doubt, you can ask. Tomorrow I'm going to call someone randomly. In your textbook, what is the link I got sent it? The page number 255 on this problem 3.14. Problem number 3.14. So there they given for DAXP code. I mean the example code they given is the DAXP loop. It is a DAXP loop. One example has been given, and the latency functional unit latency is also given there. Like this, 4 things you have to do it. Okay, so how many times it has to be done? I think right the loop is going to repeat for a vector of 100 usually around. Okay, loop unrolling tomorrow you can do it. At least first 2 cases. These 2 cases you try it out with scheduling and without scheduling for that code, and you just come out with how many cycles it required to execute that loop. Okay, so got it? The problem number 3.14. So in that with cycle and without cycle, for that same code with the functional latencies, you try to show the output. So I may call anyone randomly and I will ask you. So you have to do it. The other case is right, or else you take it, unroll the loop for 10 times. So it is 100 elements. You unroll the loop for 10 times. You read the question. It is there in the textbook. Yeah, for this code. Is it visible? Guys, is it visible?
Yes, ma'am.
Yes.
Now this code, just note on this page number 256 for this DAXP loop. You try to calculate all those things. This is a vector of length 100 and unroll the loop for 10 times and you just find out how many clock cycles is required. Got it? So for this problem, and the functional table is also given below. Functional latency table is also given here. So based upon that, right, you try to do it. Okay. So tomorrow, you try to finish it up. Definitely you may get one problem. So for that, I'm saying. Because tomorrow I'm going to start the next topic, branch predictions. So you just practice this in your code. So if you have doubt, you can ask me.